Welcome back to Introduction to Formal Logic. We're going to be covering truth tables for negation, conjunction, and disjunction. You've already covered what operators are, how they function, what they mean. We're going to be doing some of the same things that we covered in the last lesson, but doing it differently. And more importantly, we're going to be covering a new technique that you can use for figuring out all kinds of sentences, arguments, how the operators work. All right, so let's get into specifics. What can you expect from this lesson? Well, now that you have already learned what an operator is, and a little bit about how they work or they function, and also what they mean, right? The syntax, how they work, how they function, the rules involved, and also what they mean, the semantics or the interpretation. You're now going to learn more specifically about how they function by using what we call truth tables. This is the skill that you're going to be coming away with after this lesson. You will know a lot about truth tables. All right, we're going to use them, and we're going to use them later on as well for other lessons. So you're going to learn how to interpret and also to construct truth tables for the 5 operators. We're going over the basics of truth tables and also the basics of the operators in a different way that we weren't able to go over last time because you didn't know how truth tables worked, what they are, etc. All right, so let's dive into the lesson, figure this out. What are truth tables? So here's how we're going to start. We're going to start with negation. The simplest operator, negation. So here's what the truth table for negation looks like in the truth table below. All right, you see it. We're going to interpret it. I'll explain what everything means. Let's interpret it. On the left side of that table, the left side, we have, and this is going to be the case for truth tables in general. All right, so I'm setting it up, and we're going to be using this negation as just an example. It's going to get more complicated, but we're going to be starting very simply. All right, so on the left side of truth tables, we have our stock of atomic sentences. Remember from the last lesson, an atomic sentence is just a sentence that can't be divided into further parts, whether that part is an operator or another sentence. All right, so an atomic or simple sentence. So in this case, we only have one atomic sentence, and that's going to be P. And then we have all of its possible truth values under that first column on the left. All right, so again, recall the difference between an atomic sentence and a compound sentence. All right, we went over that, so make sure that you have that down. So if I was fussy about technical details for the more advanced logicians, I would make that P a Greek symbol because P could actually be a particular sentence or instance in our logical language. You remember last time we let P represent different kinds of sentences. All right, and we can do that again. So if I was going to use something that can't be used in our logical language to represent a sentence, I would use like a Greek letter. So if you see that in logic textbooks, that's why they use Greek letters sometimes. They're called meta variables. You don't need to know that. But anyway, so we see P on the left-hand side, right? That's our stock of atomic sentences. And then you see all its possible truth values right there on the left, true or false. So that's the left side. On the right side, we have our compound sentence that we want to interpret with all its possible truth values that are then calculated from using our atomic sentences on the left. All right, so the truth values of the atomic sentences then determine the truth values of the compound sentence. Another way to say that is that the compound sentence's truth values are a function of the atomic sentence on the left and whatever we're doing on the right, in this case, negating that atomic sentence. Okay, so this is going to be clear as we move along. So what do we mean? A truth table, like the one that you see there for negation, it's a visual and automated tool that shows every possible way that the truth value of a compound sentence is determined. Or a function of, we talked about that last time, it's a function of the truth values that you see there of our atomic sentences. It's just a truth function. Remember, we have inputs and then we have outputs when we have a function. So, for example, if our atomic sentence P is true, you see that in the truth table right there on the left-hand side. If our atomic sentence P is true, on the left-hand side, then the negation function or operator goes to work and it flips the value to false on the right side. So it's just a function. It just is calculating, based on what negation means, the truth value on the right-hand side. All right, so that should sound familiar by now because we went over what negation means and what happens when we have a negation operator and we have that on an atomic sentence. It just flips the truth value. That's all we're saying. And the truth table is just a visual representation of part of what we went over in the previous lesson on operators. So again, same principle. If our atomic sentence P is false, you see that in the second row. That's the other possibility for the truth value for P. There's only two for P. It's either true or false. Those are all the possibilities. So we went over one, what happens when it's true, and negation goes to work or does its function, the negation operator, then it goes to false. So here in this case, in this second row, if our atomic sentence P is false on the left side, our atomic sentence, the negation function or operator goes to work and it flips the value to true, from false to true on the right side. All right, very simple. That's really all we mean. So you can see how it's just a calculation. You have your stock of atomic sentences on the left and its truth values, and then you just sort of calculate, well, on the right side, what's the operator doing? It's flipping the truth values. That's all it's doing. All right, so starting with negation. And these are all the possible combinations of truth values for the negation operator. So every possibility of truth values is represented by a complete truth table. And I'll note, you want to get these operator truth tables down in your head because they are going to be used later on in your head when you try to calculate the truth values of much more complex sentences, all right? Compound sentences that are much more complex, all right? So make sure that you have these down. It wouldn't hurt to write down that truth table somewhere, have it accessible to you for later on, and really just get that in your head. For negation, it's just not that difficult. We're gonna go over the truth values for every single, the truth tables for every single operator. All right, so starting just with one, and this is going to be the case for all the operators going forward. You are going to want to memorize those in your head so that you have them for later on when you're doing much more complicated calculations. And remember that we can plug in any statement that we want for P. All right, so I'll use our familiar example. If P is my coffee cup is full, then if my coffee cup is full is true, then it's not the case that my coffee cup is full will be false. So obviously, and again, we're representing that using this truth table here. You can sort of look at the truth values and say, okay, yeah, if this is the case, then that's going to be the case. So if my coffee cup is full is false, you see that right there in that second row. If that's the case, then right-hand side, there's the sentence that we want to interpret, the statement we want to interpret with our operator, the compound statement. Then if that atomic statement is false, then it's not the case, there's the negation, that my coffee cup is full will be true. And there you see that represented in the truth table. All right, so we're going to take a look at other examples, like I said, all of the operators, so that we have every single operator's truth table, and we can easily see how what we talked about when we talked about more generally what the operators mean and what they're doing, this is going to be represented in a truth table like you see there. Okay, so we're going to make things a little bit more complicated than they were just using negation, all right? But we're using all the same principles from the negation truth table. We're going to apply it to our and operator or conjunction. All right, and you see that there. So let me go step by step. Because the conjunction operator takes two atomic sentences, remember we call those the conjuncts, all right? So this is where terminology really is key and crucial. So hopefully you remember those terms from the previous lesson. You can apply it here. The conjunction operator takes two atomic sentences, the conjuncts, as its inputs. We have two atomic sentences represented on the left side of the table, P and Q. Because remember, the left side of the truth table, that's where our stock of atomic sentences go. Okay, so you see right there in our case, and I'm going to use P and Q the whole time here. So we have P, that column, and we have Q, that column. All right, and I'm going to explain how we can fill that truth table out with all those truth values. So in this case, like in every case, we still want to represent all of the possibilities of truth values that we have for the truth table in question that we're going to be using. So here are a couple formulas and procedures that you're going to need to memorize. Get these down, write them down somewhere if you need to, when you interpret and construct a truth table. All right, because there is, again, an automated, calculated way that we figure out what's going on the left-hand side, our atomic sentences. How do you figure out what all the possible truth values are? There's a very simple way that we can boil down. All right, and here I'm going to show you. So if you count the number of rows here in this truth table, you're going to see that there's the top row. All right, so now we're interpreting the truth table. It's a little bit more complex. It's the same as the negation, but it's a little bit more complex because we have 2 atomic sentences, and that's what makes it more complicated. There's the top row, which includes all the atomic statements on the left. So for negation, we only had 1, right? It was just P. That made it a little bit easier. Now we have 2. And then, so that's on our left side. So the top row is going to be our atomic sentences. And then we have the compound sentence to be interpreted on the right. In this case, P and Q. And there are 4 rows of truth values. Okay. And there's a formula for figuring out the number of rows that you're going to need for truth values. What you do is you take the number of atomic sentences. In our case, it's just 2. There's P and there's Q. 1, 2. That's it. P and Q. And whatever that number is, the number of atomic sentences in the truth table that you're calculating and interpreting, that number is going to be the exponent of 2 that you're going to calculate to get the number of rows. So in this case, it's going to be 2 to the second power, or 2 times 2. That's the exponent there, which is 4. And if you don't know how to calculate exponents, or it's been a while since you did it and you forget exactly how it works, that's okay, because I'm going to show you in each case. All right, so think of this as a nice shortcut. It's a really easy way to figure out, okay, how do I figure out the number of rows in this truth table that I'm going to be building? This is the way to do it. All right, but if you want to just simply memorize that for truth tables with 2 atomic sentences, you're going to have 4 rows. All right, so that's pretty easy to memorize. Once you get more atomic sentences, when things get a little bit more complex, this is going to be a nice shortcut tool so that you can just do a quick, okay, what's the exponent? I'm going to calculate it when the rows get a lot longer than just 4. All right, we'll get to that later. All right, but this is the formula. So make sure that you have this down. This is how you calculate the number of rows in a truth table. Here we have 2 atomic sentences. That tells us how many rows we need for our truth table. So once you have the top line and then the number of rows, you can start automatically filling out the columns of the table to get all the possibilities. All right, so there you see the truth table already filled out. So far, the only thing that I've described is the top row and the number of rows. All right, so what I like to do is I like to start at the atomic column farthest to the right. You can do left if you want, but here's what I do. I like to start at the atomic column farthest to the right. Now we're still on the left-hand side dealing with atomic statements. We're not on the right-hand side of the truth table yet. We're on the atomic side, farthest to the right on that atomic statement side. And then you alternate truth values by 1 going down, starting with T. All right, so you see that column under Q. That's really where I'm starting. All right, so I start with true, and I alternate truth values by 1. So I start with true, and then I alternate false, then I alternate true, alternate false, going down, starting with T, okay? So hopefully you're following, right? I was just under Q, started with T, alternated by 1, And now that column is filled out. Then I go to the column to the left of that column that I started with. In this case, that's the P column. And then I'm going to alternate truth values by 2 going down. You'll see why. So I start under Q, alternate by 1. I move 1 column over to the left, and then I alternate truth values by 2 going down, starting with T. So look under P right there, that truth value column. I start with T, and I do another T because I'm alternating by 2 here. So T, T, that's 2. And then I alternate another 2, false, false. All right, and so now that row is done. So following that formula is going to give you every possible combination of truth values for each row. Just like we did for negation. You see the truth table for negation there, right? I did the same thing. So if you look at what I said before, so I like to start at the atomic column farthest to the right and alternate truth values by 1 going down starting with T. That's what we did for negation too. I just didn't tell you how that works at the time. So if you look at P under that negation truth value, there's P. I start with true, and then I alternate by 1, false, and then that's it. All right, I do the same thing over here for P and Q. That's how you set up the truth table. Okay, so I know that it's a lot of details at this point. Hang in there. You'll get it. Want to go step by step, and you'll quickly, I think, figure out why are we doing it in this way. So now that we've constructed the truth table for conjunction, we can interpret it. All right, so we've got the top row. We described how we get that. Then we got the atomic sentences and all the possible truth values on the left, how we get that. Now let's interpret it. All right. So the column under the compound conjunction that you see there, P and Q, the conjunction sentence, that's what we're interpreting. We're doing the truth value for the truth table for conjunction. So row by row says that if P is true, see that first row all the way to the left? If P is true and Q is true, then now we have our compound sentence interpretation. The whole compound conjunction sentence is true. Now, you know that from what we went over talking about how operators work, specifically the conjunction operator. You know by now, because you memorized it, you're good to go on that, that in a conjunction needs all of its conjuncts to be true in order for the entire compound sentence to be true. And this truth table visually gives you a representation of that meaning. All right. So again, all we did was look at that first possibility or row. We want to think of rows as like possibilities. We said if P is true and Q is true, then what's P and Q? It's going to be true because all its conjuncts are true. And we represent that using that truth table right there. First row, taken care of. Okay. Now, if P is true, now we're on the second row. If P is true and Q is false, you see that on the second row, that's the next possibility or row. Then if that's the case, the whole compound conjunction sentence is going to be false. Why is that? Because, again, a conjunction needs all its conjuncts to be true in order for the compound sentence to be true. And if just one is false, that's it. The whole compound sentence is sort of ruined, right? It's going to be false. Okay, so there's the second row. By now you should be seeing a pattern. If P is false, now we're in the third row or possibility. If P is false, you see that F in the third row starting out all the way to the left. If P is false and Q is true, then the whole compound conjunction sentence will be false. So if P is false and Q is true, then we have a false in there. The whole thing's going to be false. All right. And you can see the next option too. If both P and Q are false, then the whole sentence is going to be false, obviously. Okay. So remember that the truth table exhausts every possibility of truth values for the atomic sentences and the compound sentence. Those are all the possibilities. We don't have a possibility remainder here at this point. So for conjunction, note that just like we said before, a conjunction needs all the sentences that make it up, all of its conjuncts to be true for the whole sentence to be true. By now, that should just be burned in your brain. That is what conjunction in propositional logic means. That's its interpretation, okay? And remember, we talked about how semantics or interpretation, it's going to be different from ordinary English. We're concentrating on truth values here. So if P represents my coffee cup is full and Q represents my water cup is full, for example, then the only time the whole compound sentence, my coffee cup is full and my water cup is full, is true, that whole sentence is true, is when all of its parts or conjuncts are true. All right, so hopefully you completely understand conjunction at this point and what the truth value, better, what the conditions are for that compound sentence to be true, and then what the conditions are for the compound sentence to be false. All it needs is just one conjunct to be false, the whole thing's false. Okay. So if my coffee cup is full is true, and my water cup is full is false, then my coffee cup is full and my water cup is full will be false. All right, that whole statement will be false. If any of the conjunctions are false, the whole sentence is false. And so this is a case with conjunction where it follows pretty closely to our English meaning of and. All right, and we saw that before when we did a more sort of zoomed out interpretation of conjunction. All right, so we covered negation, we covered conjunction. Let's take a look at disjunction or and see what happens there. So you're going to see that the truth table looks pretty similar to the conjunction one, except for on the right-hand side there, we have our disjunction, obviously, because that's what we're focusing on right now. We're going to use all the same principles that we use for negation and conjunction truth table, and now we're just going to apply it to this particular operator or disjunction. All right? So I won't labor as much on every step at this point because hopefully you're, again, starting to see the patterns. You're going to do some pattern recognition throughout this whole course, and you're going to see where this matters. Right now, it matters. So understand that we're just applying the same principles that we covered before to disjunction. So because the disjunction operator also takes two atomic sentences as its inputs, so we again have two atomic sentences represented on the left side of the table as P and Q. And remember, I could have chosen any other letter, but it's pretty common to stick with P and Q just because they're easy. So again, we have the same thing going on there where our atomic statements are the same as in conjunction, P and Q. So we set it up in the same way. We still want to represent all the possibilities of truth values. Those are represented below, as you can see. So we use the same formula that we covered last time for figuring out the number of rows that we need for the truth values. You take the number of atomic sentences, and again, in this case, it's going to be 2. Remember, for negation, it was just 1. In this case, 2. It's P and Q. And that number, in this case 2, is going to be the exponent of 2 that we will calculate to get the number of rows. All right, so again, 2 to the second power. 2 is that exponent there. And that's just 2 times 2, which is 4. All right, so we have 4 rows. So I'm just explaining at least that part again. All right, so let's look at disjunction. So once we have the top line and the number of rows, you see, if we want to take a look at the truth table for disjunction, you see that our top line on the right side, that's going to be where the compound sentences come in this case, disjunction. We start just automatically filling out the columns of the table to get all the possibilities, all right? So once you get these truth tables down, you're going to eventually be at a point where you're just automatically filling everything out. You're just going to be calculating. It's just going to be automatic. All right, so again, take a look over there. I like to start at the column farthest to the right on the atomic sentence side, that left side, but the column all the way to the right on that left-hand side. And then alternate truth values by 1 going down, starting with T. So you see that under Q. Start with T, alternate by 1, T, F, T, F. Second column. I go to the next column to the left and alternate truth values by 2 going down, starting with T. So then I go TTFF. All right. So first column all the way to the right, atomic sentence, TFTF. Second column, the one that's to the left of that one, TTFF. That's how it's done. You see it's the same exact way that we did for conjunction because we have our same stock of atomic sentences because both conjunction and disjunction take 2 atomic sentences. All right? So following that formula that I've now described a couple of times, it's going to give you every possible combination of truth values for each row. Just like we did for conjunction, you can see the similarities there. All right, but you see the differences on the right-hand side. Disjunction means something different in propositional logic, obviously, than conjunction. All right, now that we have constructed the truth table for disjunction, there you see it, we can interpret it. It should be familiar by now. The column under the compound disjunction sentence, row by row, says that if P is true, reading from all the way to the left to the right, if P is true and Q is true, then the whole compound disjunction sentence is going to be true. You know that from the meaning of disjunction. If P is true and then Q is false, then again, the whole compound sentence is going to be true. All right, there you see it represented in the second row. So if P is false and Q is true, again, we have one atomic statement that's true. It's all we need for the whole compound sentence to be true. Then the whole compound disjunction sentence is going to be true in that third row. But if both P and Q, in other words, if all of our disjuncts are false, then the whole sentence will be false. And you know that going into it because you know the meaning of disjunction, and that meaning is going to be truth functional. It's going to be what happens when its parts have a certain truth value. Well, it's going to spit out some output of another truth value. Okay, again, remember that the truth table, whatever truth table you're talking about, it's going to exhaust every possibility of truth values for the atomic sentences on the left-hand side, and then the compound sentence that you're looking at on the right-hand side. Every possibility of truth value is covered. So for disjunction, note that just like we said before, a disjunction needs only one of the sentences that make it up, or again, what we call disjuncts. It only needs one disjunct to be true for the entire sentence to be true. That's all it needs. And that is what disjunction in propositional logic means. All right. And it's represented there by this truth table. So again, taking our familiar example, if P represents my coffee cup is full, we'll stick with that, and Q represents my water cup is full, then the only time that the whole compound sentence, my coffee cup is full or my water cup is full, is false is when all of its parts or all of its disjuncts are false. In that case, the whole thing's going to be false. You see that represented there, right? You see on the right-hand side, it's true if both are true. It's true if only one is true. It's true if only one is true again. It's going to be false if they're all false. All right, there you see that truth table visual representation of the principles that we talked about before, sort of zooming out more broad and abstract. So if my coffee cup is full is false, and my water cup is full is false, then my coffee cup is full or my water cup is full will be false. If both are false, again, the whole sentence is false. And this also follows pretty closely our English meaning of or. All right, so this is where there's a lot of similarity with how we're used to or being translated and how it's translated in what it means in propositional logic. So next, we're going to take a look at the truth tables for the conditionals, material implication that we sort of interpreted in the previous lesson, and then also the biconditional.